In example 125, we've got another hypothesis test, and this is going to be a hypothesis test that is two-tailed. The last one we did was a one-tailed situation. So here we have a manufacturing process that produces ball bearings with diameters having a normal distribution and a standard deviation. Sigma equals 0.04. Ball bearings that have diameters that are too large or too small are undesirable. So we don't want to be off too much in any direction, and that's what makes it two-tailed. So we're going to test the null hypothesis that mu is equal to 0.50 centimeters. And now there's no inequality that follows the null hypothesis this time because we could have error in both directions. A sample of 25 randomly selected, so n is 25, and the sample mean, x bar, is found to be 0.52. So is this enough to conclude that we think that the population mean is not equal to 0.50, or is this off in too much for us to stick with our assumed value of mu? So H naught is mu equals 0.50. The alternative hypothesis is just that mu is not equal to 0.50. We could have error in both directions, and so that means when we set about finding our critical region, we know that our critical region exists on both sides. So alpha is 0.02. And in a two-tailed situation, alpha is the total error that we could have. So that means that since the error exists in two tails, it's going to be half on either side. So this is 0.01. And over here, this area is 0.01. And so we have some critical values here that we need to find. Because of the symmetry, we know they'll be plus or minus the same absolute value. So whatever, if we just find that negative one, we know that the other critical z-score is going to be the positive value. So just as we did before, we're going to use our table to figure out what this critical value is. And all we need to do, since we know this particular, looking at that particular side, we know that the total area to the left, right on the left tail of that negative critical z-score is 0.01. So let's go to the table and look up as close to 0.01 as we can get. So 0.01 looks like the closest we're going to get is right here at 0.0099, and that has a z-score of negative 2.33. And that means that this other critical value here is positive 2.33. So we know our critical values that bound our critical region. So the next thing we need to do is sort of figure out what is our test statistic, that z-star, the z-score for the sample mean of 0.52. And so let's write out our formula. X bar minus mu divided by sigma over root n. And let's compute sigma over root n first, just to make it a little bit easier to plug it in. Here's our values for sigma and root n up here. So 0.04 divided by square root of 25. Square root of 25 is 5, we get 0.008. So there's our sigma over root n. That's going to be our denominator. And x bar minus mu. X bar is 0.52 minus 0.50. So this is 0.02 over 0.008. So let's see what we get for z star. We get 2.5. So z star is equal to positive 2.5. Now let's compare that value of z star to our critical values. 2.5 is greater than 2.33. So that means our z star is right here, sitting right inside the critical region, and that means we need to reject the null hypothesis. Right, it was too far away from our assumed mean value of 0.50, and so we reject the null hypothesis, and our conclusion will be that there is sufficient evidence at the 0.02 level of significance that mu is not equal to 0.50 centimeters. There's our hypothesis test.